Good morning, all. Welcome to the week 12 doubt clearing session for Fundamentals of Additive Manufacturing. This is the last session for this course. I hope everybody has learned at least a little bit about the basics of fundamentals of additive manufacturing because it's a vast topic, it's a new topic. So, day by day, the research and the technology, the advancement is going well in this or going advanced in this field of additive manufacturing. So let's start today's doubt clearing session. I hope you are watching this video on YouTube, and if you have any doubt, you can put it in in the comment section, or you can mail me anyway. So let's share my screen. So today we are going to talk about the topic that has been covered in this week 12's lectures. Then I'll brief out the whole topic of additive manufacturing a little bit, whatever has been covered, some few important points I'll be discussing, and lastly we will solve the previous year question. So in the last, I can go with the class notes as well. So, in the first lecture, we are going to talk about the electron beam melting. So, in week 11's lecture, we have seen first the completion of the topic of DED, directed energy deposition, where the powder and laser come simultaneously and they meet at a certain point over the build plate where we can get the highest capture efficiency. Capture efficiency is nothing but the amount of powder getting melted and making track by the whole powder which was supplied from the hopper. So basically, it is an efficiency to see how much powder has been utilized among water coming, because the powder is cu- or the powder is blown with the help of a carrier gas, and because of the gas, sometimes it may happen because of the high flow rate of the gas, the powder is not coming, the powder is coming, it is reaching the melt pool, but because of the high velocity of the or flow rate of the gas, it is getting bounced back, it is getting reflected back from the melt pool, and because of the bounce back, the melt pool is not actually engulfing the powder particles, so it is not melting all the powder particles which are coming in the melt pool. So that's why capture efficiency is very important in case of DD. Then, then we have talked about the starting of LPBF. First, PBF, powder bed fusion. Powder bed fusion means the powders will be kept inside a chamber, inside a container, which you can call it as dispenser or supplier. From that dispenser of supplier, the powder will be spread over the build plate using a recoater. In case of DED, the nozzle design is very crucial because the powder is coming through the nozzle, the same nozzle which is also used for the laser delivery. So that's why nozzle design is very important, or cladding head we call it. So that cladding head design is very helpful. It is very useful because when the powders also come, they also will meet over a certain point, and that will be the focus of the powder. And the laser beam will also has its focus and defocus point. Now you have to match the defocus region of laser and the focus point of powder in such a way that the spot area is uh, containing maximum number of powder, so that maximum number of powder particles which are coming from the hopper can be utilized in the melt pool. so that your capture efficiency will increase. So this is the concept of DD, and in LPPF recoater design is very important because recoater is the one instrument which is actually responsible for good quality. Means the other parameters are also there, other process parameters are also there, but recoater has a very important role in PBF as it is called powder bed fusion. So over the powder bed or over the build plate, the powder is spread and the powder bed is made. So the spreading is very important. If the spreading is not uniform, first point. Second point, if the spreading is not uniformly 30 micron, spreading an uniform layer is not that tough if it is 10 millimeter, but spreading an uniform layer over a flat build plate with 30 micron layer thickness or 20 micron layer thickness is very difficult. So that's why powder bed fusion is a bit critical process. It is crucial also in terms of the accuracy because it is critical, but you have to use it if you are really interested to work in additive manufacturing process where you can get the highest accuracy out of it. So that is the difference between PBF and DD. So there is another difference also in PBF and DD. PBF is used for very high accuracy, I said. So as a result, the layer thickness I am taking here is 30 micron. To get the 30 micron layer thickness, we choose the powder particle size distribution 10 to 45. Okay. Now let's try to understand that why it is 10 to 45. Why it is not other than that? Because there can be two contradictory sentences. One is the layer thickness. Let me just draw it here. If this is my layer thickness and if this is equal to 30 micron and my powder particle size distribution is 10 to 45, then how is it possible? Like 45 is this and layer thickness is this. So how can you choose large powder particle size distribution than your layer thickness? So if you see carefully, then until 10 to 30 can be filled inside that 30 micron layer thickness if you are spreading it properly. So 90% of the distribution is going inside the layer thickness. But what about the last 10%? So when you will start depositing the material over the build plate layer by layer, this is my build part. So in micron level, there will be undulation over the surface or waviness over the surface after the laser consolidation. And due to the waviness, the actual layer thickness will get decreased after melting and solidification. So now when 45 micron is coming, this is my 30 micron layer thickness. The 45 micron will feel these undulated points. The part was supposed to be this and this. So the 40 micron is feeling this because now there is an undulation here because of the shrinkage. You understand? So till 10 to 30 will feel the uniform layer, and 45 after 40 after 30 till 45, those 30 to 45 micron powders will feel the undulated surface, will compensate the shrinkage of the previously built layer. The smaller particles, like towards 20 or 10, basically 10 micrometer, will feel the voids because our D90 is maybe 33. This is my 33 powders. This is my 20 powders. And these are my 10 micron, which will feel the void inside it. So this is how the distribution is useful. So how the powders are made, that is also one big question. So there are various processes. We will be talking about the processes, but before that, let's see the difference that I was talking about. That what is the difference between DD and LPBF? So as LPBF uses 15 to 45 or 10 to 45 micrometer powder, the spot dye is obviously lesser. It means that lesser spot dye laser you can use. For example, 70 micron, 70 micron or 60 micron you can use to melt that track. As a result, your track is smaller, your layer thickness is smaller, so obviously accuracy increases. But the time and cost will also increase. In case of DD, the powders are coming from the hopper. So the first condition is powders are blown with the help of carrier gas throughout the hopper and then the pipe and then until the cladding head. So the powder has to have a very good flowability. Flowability means ability to flow inside the pipe along with the carrier gas. So if you are taking lesser diameter powder, the flowability will not be good. So to maintain the flowability, we are taking the higher particle size. For example, 45 to 120. So here itself it is starting from 45. As your layer thickness, as your powder particle size distribution is higher, your layer thickness will be higher. As your layer thickness will be higher, your powder spot diameter has to be higher. So there we use 2 to 3 millimeter spot diameter. Just imagine where 70 micron is and where 3 millimeter is. So that much difference we have to be ensured about. And that is the most or biggest difference between DD and LPBF. Now let's see another variant of powder wet fusion, which is electron beam powder wet fusion. What I can recall is in my last class, I have already last class I have already discussed the electron beam melting, how it is focused using the deflective electromagnetic mirrors, electromagnetic lens, how it is different from a normal lens. As a recap, we will again study the topic of electron beam powder bed fusion. So everything will be same, only instead of laser, we are using electron beam. Now, as electrons are itself very light because they sit inside the atom. If atom is light, then electron is lighter. So as the electrons are very light and now it is focused at a particular position over the build plate. Now it is coming all the way from the head to the substrate. So in between, if it by chance hits any other particle, for example, air particle like nitrogen, oxygen, carbon dioxide, then it can get deflected. It can get deviated from its required or desired path. So that is why the chamber of electron beam melting is always supposed to be vacuumed. So this is one very big challenge because when you establish a vacuum inside a small chamber with small electron beam, small supplier, it is easy. But when you go for creating vacuum in a very large chamber, because now people will ask why large chamber, because now you want to increase the build volume. Build volume means the x and z, x and y direction length of the build plate, that is the build area, and then how much height is available, until what point I can print my sample, that is the z level, and the whole combination is called as build volume. So if you want to increase the build volume, then you have to increase the inside area of the chamber. The cost of establishing vacuum inside it will increase, will be much more difficult as well. The sealing should be proper. So step by step the money or the cost is getting increased basically. So that is why the electron beam melting is not, I wouldn't say that not that bad, but it's good, but it has some difficulties. So similarly, the powders will come. The powder. So the powder can come through the supplier. The ricotta can carry the powder from the supplier, then spread it over the bill plate. The powder can be stored inside a hopper in the overhead portion, and from that the powder can come to the ricotta. So you can use the electrostatically charged recorder also. Aerosint is one company selling very renowned recorder which is mostly used for multi-material printing. Robotic recorder also, robotic arm can also be useful for this recording technology. The same process can be used for electron beam melting as well. Because one thing I want to add is, in case of laser powder bed fusion of metals, we always try to what should I say? Maintain a constant environment inside the machine. At the time of running, you would notice 0% oxygen level inside the machine and 12.8% or something argon gas pressure. So it is so controlled, right? So already the seals are good inside a PVF machine. So you don't have to worry about much about seals inside it. But now if you are making vacuum, so seals needs to be more strong. But otherwise the PVF process is itself very costly, whether you use laser or electron beam. In case of electron beam melting, there is another difference. So the difference is, in case of electron beam melting, preheating takes place by the electron beam on the whole bell plate, through which the powders get sintered with each other and you don't need any support structure. Then this is the powder distribution graph. It follows the Gaussian nature, and you can uh, see if this is just assume this is particle size. Then hello. Yes, so I was continuing with the topic that has been covered in week 12, so you can listen to it. So I was talking about the powder size distribution. So the powder size will be this is hmm. So you assume this is how much. So by that, how much? So this is the portion. This is another portion. This is the powder distribution for DED. When it will be for LPBF, it will start with end by 45. So yeah, I already discussed in the last class that in case of electron beam melting, the electron beam is acting as an energy source, and the magnetic lenses or electromagnetic lenses are used to focus the electron beam onto the build plate, because normal lens cannot be used in case of electron beam. The electrons are very lightweight. They have to be very carefully treated and focused. So that's why, to avoid the stigmation error, to avoid any defocusing, four stigmator lenses are used. Over that, two magnetic lens, electromagnetic lens will be used to focus it. To eliminate the stigmation, stigmators are used. So there are some challenges in powder bed fusion. So one is the delamination. Delamination means your layers are not getting fused with each other properly. They are getting delaminated. So there will be unfused area or zone in between subsequent layers. That is basically because of poor heat conductivity and lesser energy density than what is required. Then, due to keyhole mode effect, there can be instability in the melt pool, there can be porosity formation due to the high power but low energy density, because your scan speed is very high. So if your laser power is very high than usual, than what is required, and then your energy density is less, then you will see balling effect. That is mostly visible in case of DD, because in case of powder bed fusion, your layer thickness itself is so less, balling effect is very rare. If you are going with very much bad process parameter, then only you will get balling effect. Otherwise, balling effect is not that much, like, not easy to create as a defect in PBF, but in DD it is very common, very very common. So there are some challenges, that these challenges were regarding the PVF process, whether it's laser or electron beam. But these next challenges are regarding the electron beam melting. So, one is if there is any humidity entrapped in your powders, that will disrupt the process. That is also one defect considered in LPBF process. But in case of electron beam, as you're working in vacuum, that will be more problematic. So the electron which is gathered then cohesive force of the powder particles. So the momentum of the electron which is greater than the cohesive force of the powder particle will just deflect the powders from its original position. It can just make the powder particles bounce back from the melt pool. And also another is the electrons are coming, hitting the powders, so the powders can get electrostatically charged. And as electrons are negatively charged, the powders will get negatively charged. And if now all the powders are negatively charged, they can repel each other. So that is again one another problem regarding this process. So if your electron beam is penetrating inside the metal, you'll get a very beautiful melt pool profile. But again, as the layer thickness is very less, it should not be like your penetration depth inside the melt pool is very high. So that also you have to control. Now, after electron beam melt, after or apart from these defects, electron beam melting is almost same like powder bed fusion. There is another variation of powder bed fusion. So under the state of the art, if you can remember, there was seven state of the art classification of additive manufacturing. Their powder bed fusion was one type of additive manufacturing in which laser beam melting or electron beam melting is are two of the very popular process. Other than powder bed fusion, there was another state of the art called binder jetting, which uses very lesser power. It was it because it was towards the first side of the classification, towards the left. So this binder jetting is also another state of the art additive manufacturing technique. I hope my slide and the PDF was visible where I was talking. Kiran, if you have any doubt, you can ask. Or you can put it in the comment section. Because this is gonna be our last class. Okay. So, in case of powder bed fusion, if this is a top view of the powder bed, excuse me, then your powder is spread over the build plate, throughout the build plate. These are powders, huh? Fully covered. Your electron beam or your laser comes, they melt the powders present over there and they fuse it. Here, fusion is taking place by melting. At the same time, if I talk about binder jetting, powders are spread over the build plate, and then from the head, the binders come. The binders come, get deposited over the build plate on those position where the part needs to be built. So wherever it is desired, it is required, the droplet of the binders will come and gets deposited over the build plate. And this is how binder jetting works. I'll have some. So that is the basic difference between PBF and binder jetting. Here the binders are coming. So binder has to be liquid. So the finish of the binder jetting parts are really good. Really good. The problem is with the density, because here you are not melting, so you cannot ensure the 100%, or 100% is not even possible in any additive manufacturing, but at least towards 99% or 90% density also you cannot uh, aim in case of binder jetting. As I said, this is not a fusion, or this is a fusion, not, this is not a melting. In case of powder based additive manufacturing, powder bed and powder fed, two types of additive can be there. Powder fed, in powder fed, DD. It can be laser based, it can be arc based, it can be plasma based. In powder bed, it can be PBF with laser based, electron beam based, plasma based, and there can be binder jetting. So this is the binder jetting we are going to talk about. So in case of binder jetting, the joining process is fusion with the help of binders. Powder material is used. Scanning system. So basically, there is no laser or optical component. So it's generally easier to send the ink or the binder material from the head rather than going for multiple lenses to focus an optical light source. Powder delivery system can be same, like it can be like the powder will be stored in a container called supplier or dispenser. It will move up, the recoater will spread the powder over the build plate, or the powder will be stored in the hopper in the overhead position, and from the overhead the powder will come in the recoater itself, and recoater will spread the powder. Electrostatically charged bed can also be used. Built atmosphere is not that important here, and built platform has to be metal. So there can be multiple uh, system under this binder jetting, but the state of the art is binder jetting. So there, if you see, this is the powder and this is the part. So basically, layer by layer, the binder is getting generated or deposited, and your part is made. So the powder delivery is not that much critical because it's same as powder bed fusion, but the binder delivery is here the problem. So if you are depositing the binder with single nozzle, then time of the process will increase drastically. So you have to optimize that thing. How to optimize? So you can go for multiple nozzles for the binders or ink type of binders, whatever is it. Or instead of single nozzle, you can use multiple nozzles. So in case of powder delivery, top fitting, bottom fitting, we already know. In case of powder recoating system, blade roller slot feeder, we already know. Only thing is scanning system. So wide choices of powders and binders are possible. The binders can be mixed with other materials. Also, different materials can be dispensed by different print head. Therefore, multi-material is possible. So here, as binder is getting dispensed from the head, that is also known as ink head or binder head. So what I want to discuss is that your compaction of the part, your density of the part will to some extent depend upon which type of binder you are using. So if you are going with single nozzle, then only one binder. If you are going with multiple nozzle, then multiple binder materials you can use. And if you are using same binder, then multiple nozzles will reduce your time. But what if we give different binder compositions? Then what will happen? So basically, the biggest influential process parameter you are changing binder composition. Your densification of the part will be different for different binder material. So as a result, you can get different densification in a single part by the means of changing the binder. Now, what will you do with that? So, in case of what do you call it? Lattice fabrication for any bridges or trashes or any other application. So, in case of lattices, when you try to make lattices for real application, you don't go with same density. Sometimes we go with solid cubes with lesser density, not throughout the part, but lesser density, where the part is not subjected to any external load. Where the part is subjected to external load, there you increase the density to increase the strength. So this is the concept of heterogeneous print. So that heterogeneous printing is possible in case of laser and electron beam. How? Just by changing the process parameter, by just changing the laser power, scan speed, these things. Because there is an optimal process parameter by which you can print the highest density part. So that's why by changing that, you can change the density of the part. So similarly, in case of binder jetting, you have to uh, know that how things go on. So once uh, I mean the binders, where is it? I'll show. Yeah. So ceramic, polymer, metal, multi-material, everything can be used. And in multi-material, even if you can go with multiple metals or metals mixed with polymers or ceramic. So you can go for multi-material printing, bimetallic printing, or metal matrix composite printing even. So the example or the advantage of binder jetting is same as LPBF. Only the problem is the densification of the part. So that's why sometimes in some machines you will see that after recoating, maybe a doctor blade is used to recoat the powder over the build plate with that 20 micron, 30 micron, and then after the binder comes consolidating, not consolidating but fusing the powders together, one roller will be pressed. One roller will be used. That roller will roll over the part and it will give a certain value of pressure so that the part can be densified. Even if there is gas porosity, even if there is humidity, that can be avoided. So that is the concept of different metals. Now here we are talking about the binder particle or binder droplets which are coming. So other than binder jetting, there can be another process also, inkjet printing. So what is inkjet printing? How the uniformity of the layer thickness will be maintained. So you remember in case of LPBA for electron beam melting, how it was maintained. So the recoater will ensure that the recoater will spread the powder uniformly over the weld plate. After that, the binder is coming from the overhead nozzle, and drop by drop it is getting deposited over the weld plate. Similarly, we have used the laser also. The laser was coming and it was scanning the part, melting it, and solidifying it. So, if laser can do it, binder will be an easy option to do it, because in case of laser, because of melting, there will be some shrinkage. But in case of binder jetting, there will not be any shrinkage. So that will ensure better uniformity in the layer spreading and the part quality. So that's why the part quality is very like finished part you'll get after binder jetting process. So as I was talking about, for the binders, the nozzles will be different than obviously laser or electron beam or plasma or any other source. So there, the droplet can be coming with two different ways. One is continuous, one is drop on demand. So there is another type of additive manufacturing also, which is not that useful for bigger parts. It's useful for moems, names, device, some chip, some diode. So that small scale parts, there we use this continuous and drop on demand process. Continuous means continuously the ink droplet will come and the nozzle is moving over the build plate. So the droplet can come more, like there can be excess amount of droplets which are coming from the nozzle. Other can be drop on demand. So to minimize the cost of the machine, cost of the material, and to ensure that the material is coming only at that position where it is needed, the drop on demand process was invented. So in case of drop on demand, you have to use a piezoelectric material. So you can see the picture of it, I think. Yes. So there is a piezoelectric material by applying by the application of external voltage, the piezoelectric material shrinks or expands. So as you are now increasing the voltage or decreasing the voltage, externally applied voltage, that piezoelectric material can be shrinked or expanded. And for example, if there is a scenario that if it is shrinked, then the drops will come. If it is not shrinked, it is expanded, the drops will not come. Then you control the voltage in such a way that piezoelectric material will shrink and expand, and accordingly the droplet will come only when it is demanded. So thermal head is like you're increasing the temperature by the externally applied voltage. Is a lower cost than the piezoelectric one. Printing rate is higher, but piezoelectric may you have to first give the voltage, then it will contract or expand, and then the drop will come. So obviously time taking process, which is again in turn increasing the cost. Risk of exposure of binder to thermal stress is there because thermally the droplets are coming hot, but there is no such case in case of piezoelectric. So otherwise the binder jetting is completely same like LPBF. This is one nozzle in which you can use the continuous or thermal or piezoelectric. But instead of one, you can go for multiple nozzles. Then your printing time will be decreased. So that is all about binder jetting. There are various companies who are selling binder jetting and with their different process setup. So that's what was discussed. Now let's have a recap about the whole course. So I would like to ask you that, or I would request you to comment on the class topic that has been covered or any question. I understand that the layer thickness includes power particle and binder layer thickness. Will it vary from other process? No. Okay. Layer thickness will not be varied. Layer thickness will be same as powder bed fusion, that 10 to 45. And as you are now dipping the droplets of ink, obviously your droplet will be very small. So your layer thickness should be very smaller. Is that answering your question?
Yes, madam.
Okay. So one thing I will repeat, I was discussing when you were not there, is this one. So the concept is you use 10 to 45 particle size distribution for 30 micron layer thickness. Now you can say that from 10 to 30 micron powder particles will fill the 30 micron layer thickness. Then what is the utility of the 30 to 45 micron powder particles? So when you deposit the layers, there will be shrinkage in the previously deposited layer. So now that 30 micron is not 30 micron, the previously deposited layer. There will be undulation. There will be this kind of valley in the previously deposited layer. So that 45 micron or 30 to 55 micron powders are used to fill those shrinkage compensation. So they are acting as a shrinkage compensation, and then your 30 10 to 30 micron powders sit in between. 30 microns fill the layer thickness. It ensures the uniform layer thickness. 10 microns particles fill the void in between the bigger particles. So that is the utility of using a distribution instead of one particle size, and that is the utility of using a little bit higher size distribution than the layer thickness. So I think that answers your question as well, and now you're clear. So, yeah. Other than that, if you have any doubt, please let me know, because I will end the class early today because I need to travel. I am going back to India today. Finally, after 3 months, after taking this doubt clearing session, 3 months outside the India, I am going back today. Maybe I'm little bit sleepy today because it's 7 a.m. here. So I class started the class at 6:30 today because of the time gap. So you can ask in between whatever doubt you feel or whatever topic you want me to discuss now. Other than that, I have the previous year question for week 12, but that is not that important. What is important is to understand the basics of fundamentals of additive manufacturing. Previous assignment question discussion. Okay, actually, I don't have the previous week assignment right now with me. If you have any particular question in your mind, you can tell me. Otherwise, I can discuss the uh, previous year week 11 questions if that can help you. I don't know. You suggest me. Week number 12 required. Yes, yes. Previous year assignment. No, yes, that I am going to discuss now. So first I'll discuss the previous year assignment, and then we can discuss about some more topics if time permits. So achieving a smaller focal spot diameter of the case of electron beam is difficult. Okay. Uh, is difficult as compared to lasers in powder bed additive manufacturing due to the repulsion of electrons, because in case of laser, if this is the lens, if this is the laser coming, the laser basically containing small photons which are not having charge, so these are photons, these will not repel each other. But if this is a electromagnetic coil which is making the electron beam focused, then inside it, these are electrons which are moving very fast downwards to the focus position. All electrons are negatively charged, so they will repel each other. And as they are repelling each other, these electromagnetic coils are used to make them positioned as their way on their way only. But it's very difficult to position because they are continuously repelling each other, so that's why the focus spot die increases. So achieving a smaller focus diameter is difficult in case of electron beam. Preheating in electron based powder bed additive manufacturing is generally achieved by scanning the print bed with a lower power density electron beam. So for each layer, in case of electron beam melting, the electron beam will come with a slightly lesser, not slightly, but very much lesser power density. It will scan the whole build platform, kind of a sintering, very loose sintering, so that heat dissipation ability increases, heat conductivity increases, and also build plate preheating is done so that the residual stress will be lesser in this case, and you'll get better part. Also, the support structure is not needed. So these are the advantages of electron beam melting over laser based powder bed fusion. The method of powder additive manufacturing crushes and grinds to achieve the smaller powder particle size, whereas something is used to achieve regular spherical. So gas atomization is for spherical powders. Gas atomization में क्या होता है? So there can be a chamber and the gas is flowed inside the chamber with high pressure, and the metal is coming in this the liquid metal is coming as soon as it reaches here. Due to the highly pressurized gas, this chamber is like this. So the metal particles will be forming droplet, and now they will get attached to the wall of the container because the gas is blown very with a very high energy. So as they are now stick to the wall, but they are droplets, so they will roll in the wall, and then they will come back, like roll and then come back to here, and this is the exit. And when they come out, there will be perfectly spherical balls of metal. So perfectly spherical metal powder. And pulverization is the electrical process, cathode anode, and then melting the material, and then but uh, these two are different, and gas atomization is mostly used in case of at least additive manufacturing. So the combination of small and big powder particles is often used in electron beam powder based additive manufacturing because, which I have already discussed, reduce the shrinkage, bigger size is used, lower smoking of the powder, and increase the powder packing density. So, all of the above. For the case of electron beam in powder bed based additive manufacturing, the vertical distance between the anode to the maximum diameter of the diverse beam is called as objective distance, and the vertical distance from the maximum diameter of the divergent beam to the minimum achievable spot diameter is the image distance. Which of the following apparatus is typically used for beam correction in electron beam based powder bed and additive manufacturing? It's stigmator. So which of the graph following is correct? Represent relationship between the focal length and the magnetic field in case of, so the last one. So these are few equations and graphs you will see in the lecture while you will watch the lecture. So delamination and spherical porosity are the two defects. Delamination, I have already told you, the heat dissipation is not taking place correctly. So there is gap in the layers. So the layers are not getting fused with each other. That is because of the thermal gradient, lesser power density than what is required. And spherical porosity is because of gas entrapment, obviously. Which of the which of the following is the reason for powder smoking? So electrostatic charge on powder particle will come make the powder particles electrostatically charged, and then they start repelling. And when the electron beams go inside the atoms, like go inside the powders, they can make the inner side powders also electrostatically charged. And when they will make it charged, they all will be like negatively charged. They will start repelling, and that's why powders tend to bounce back from the melt pool. So then there can be humidity in the powder, there can be high momentum of the electron which are bouncing back, which are making the powder bounce back from the melt pool. So these all are the reason behind this poking. For the case of electron beam based powder bed additive manufacturing, spherical porosity is caused by trapped gas and non spherical porosity is caused by insufficient melting. So, one picture I will draw. You can see this type of holes in additive manufacturing parts. Holes are small and spherical. So there can be the defect of trapped gas. That can be the defect of keyhole effect also. But if these are like this is the porosity. Then that is because of the unmelted powder particles get got entrapped inside the porosity, or there is not enough overlapping between the tracks, hatch distance is not particular. So these are the effect, these are the cause of this type of irregular porosity. Preheating in the context of electron beam based PBF can reduce the phenomena of powder smoking, so basically increasing the conductivity of the oxide layer of the powder particles. Then a higher pack density in the context of electron beam based powder based additive manufacturing can be reduced. The phenomena of powder smoking as increase the conductivity of the bed, thus preheating charge accumulation, increase the point of contact amongst powder particles, thus increasing the conductivity. In the context of electron beam melting, generally electrostatic field is used for extraction, acceleration of the electron beam, and electromagnetic for focusing, deflecting, and correction. So you can remember it like that. The laser will be generated from the gain medium inside the laser source, and then the F theta lens will be used for the focusing. So here also electrostatic field is making the electron beam go towards the desired path, like accelerating it, extracting it from the source, but electromagnetic lens will be used to focus it. In the context of, okay, this is an equation, you have to just remember it. So in the context of EBM, the focal length of the electron beam can be expressed as in the terms of acceleration voltage E naught, magnetic field B naught, focal length F, width of the focusing coil A, and mass of the electron M, and charge of the electron. So 1 by F is the focal length, is equal to pi by 16. E is the electron charge square, A into A, width of the focusing coil, into B naught square, so magnetic field ka square, divided by M, mass of the electron, into E naught, which is acceleration voltage. Which of the following is the reason for no support structure? So it is because of the uh, scanning. So little lesser thermal gradient, loose powder particles acts as support, and minimal internal stress. And these all are happening because of the pre-scanning of each layer by the low energy density electron beam. So again, which of the following graphs shows correct relationship between focal length and lens current in the focusing coil? For the metal powders in binder based powder additive manufacturing, binder components is generally with the ink, and for monomer cements, the binder components is because concrete printing and ceramic printing and polymer printing, metal printing, anything can be done with this binder jetting. So select the incorrect statement made in the context of nozzle for dispensing ink in binder base. So completely stopping the flow of ink during printing is difficult to achieve. The stream of deflected from its path. So you can see it here. I have omitted that portion. So when the liquid is coming, it's very difficult to stop the liquid in between the process all on a sudden. So because of the gravitational force, it will come. But our part is made, and that part was very small, intrinsic, accurate geometry. I cannot allow the ink to come again. So this cup is used, which is a deflecting cup, and that cup will deflect the flow of the ink. So whatever residue ink is coming from the nozzle due to the gravitational force or due to the residue, that will get deflected and it, collected in the cup and not reach the build plate. Then deflection of the ink stream provides selective deposition of the ink to the print bed, and this deflective cup, this arrangement is needed for continuous type only, because in drop on demand, the drop will only come when the voltage source is applied. Otherwise, there is no residue that will not come. So deflection of the ink stream is carried out through an appropriate application of the electric field. Select the incorrect again. So the incorrect one, yes. Continuous type of nozzles are used for drop on demand. No, obviously, piezoelectric material is used. So select the incorrect. Thermal head employs injection of ink by locally increasing the temperature. Good. Temperature increases leads to bubble formation due to local evaporation inside the nozzle. Thermal heads are lower in the cost as compared to piezoelectric, obviously. Thermal heads provide uniform, no. Piezoelectric provides uniform droplet size. For uniform droplet size, piezoelectric is used, and for lower cost and high printing, thermal head will be used. So thank you for attending, but it's not done yet. These are my email ID. So this series of the fundamentals of additive manufacturing will be completed by today, but it's not necessary that you cannot contact me afterward. You can contact me anytime for any doubt, and if you want to discuss something, you can discuss. I'm open in email ID and in LinkedIn also. So as an exam tip, I don't really know about the exam questions, but what I feel is you just go through the graphs. Don't mug up the graphs, because in additive the graphs are very simple. So if you are increasing the lens distance, your focus ability will be decreasing. So this type of relations you try to understand, then only you can plot the graph by yourself, and or at least guess the graph how it can be. And from the pattern of the weekly quizzes, I would recommend to go through the equations and the calculations also, more specifically calculation of the focus spot diameter, compensation in the SLA process, that layer thickness compensation, those formulas. And then in case of powder bed, the layer thickness, how much in DD, how much cladding layer has to be deposited to minimize the shrinkage, how much overlap is needed for high density part to higher the capture efficiency. And then you go with the concept of different recoating system. So, how many types of recorders can be used, how they are used, what are the differences between recording system, what are the differences between DD and LPBF, and in case of electron beam melting, what are the advantages and disadvantages over PBF. In case of FDM, there were a lot of equations and mathematics regarding how the nozzle heating and how the track is coming and what will be the width of the track. In SLA also, as I have mentioned, the composition of the layer height with the supplied material. So these are few maths that I can recall right now, and you just try to solve the equations. Other than that, what can we know? Because according to me, additive manufacturing is a very, and at least this course was very nice course, but very vast topic, was beautifully described by professor, and a very in-depth information has been given. So you go through all the lectures one by one, try to understand it. Otherwise, it will be difficult to answer. In between, whatever doubt you face, you can tell me. And if you want me to discuss any other topic, that also you can tell me right now. No? Uh, I think if you don't have any doubt, then I can stop my class here. As I already have mentioned, I have to travel today, and it is gonna be a 12 hours straight travel. So maybe if you don't have any doubt, then only I can stop the class. Otherwise, I will continue. Tell me. And also, don't forget to put the feedback in the feedback form. And while you are filling the feedback form, kindly write my name, that you are attending this lecture under this TA and you have felt this. These are your suggestions, or these are good thing or bad thing. Whatever you feel it. That will be helpful for me as well. Okay, so if you do not have any doubt, then I can stop here a bit early today. I know. Thank you so much for attending this 12 weeks of doubt clearing session on fundamentals of additive manufacturing. I hope to see you again in some other courses if I am taking more courses under NTPTL PMRFTA ship. Hope you will have a great exam. The upcoming final exam, you'll score good. I don't know how you have attended the course, but on the previous topic, on the previous course, my students really scored very high, and they were very much happy with the teaching also, and they mailed me afterward with that some of them ranked 5 and 2. So I was happy. I don't know about this course, so let's see how it works for you. You can anytime mail me or contact me in LinkedIn. Thank you. Happy Dasera to you as well. Happy Navratri. Stay good and happy. All the best. Bye.